Okay, so today's topic is distribution of more than one dimension, and there are two parts of my lecture. This is part 1 and I will continue to part 2. In the previous chapter, we have restricted our discussion to the probability distribution of a single random variable defined on an even space. We also know that many random variables can be defined on the same even space. In many situations, it will be convenient to consider the joint probability distributions. We'll explain in the next section of several random variables instead of considering one random variable, single random variable. So let's start with an example. Let E be the random experiment of throwing a die and then tossing a coin. So you are doing two experiments simultaneously. So E consists of joint experiment of throwing a die, and the possibilities are 1, 2, 3, 4, 5, 6, and then tossing a coin. So possibilities are head and tail. So the even space omega of E is given by it's 1 comma h. Its points are 12 distinct outcomes are 1 comma h, 2 comma h, 3 comma h, etc., 6 comma h, and 1 comma t, etc., 6 comma t, 2 comma t, 3 comma t, 6 comma t. Okay, which contains 12 distinct outcomes. So a random variable x defined on omega. Let us define a random variable x on omega as follows. How will you define? So let me define xih equal to I for I equal to 1 to 6, and xitel equal to I for I equal to 1 to 6. X denotes the number on the die. So x be a random variable that denotes the number on the die. What does it represent? The first one, xih, means the points on the die. X denotes the number on the die. If it is a head, if it is a tail, so it will give you I. So in this way you can define the random variable, or you can define the another random variable y as yih equal to 0 for I equal to 1 to 6, yitel equal to -1 for I equal to 1 to 6. So if there is a head, the random variable takes the value 0, and y equal to -1, that is the random variable will take the value -1 if tails appear. So this way you can define the random variable of a joint experiment, compound experiment. Here we see that the even head appears cannot be described solely by x, and the even number on the die is I, cannot be described solely by y. Okay, so we it will be convenient to consider the two-dimensional random variable xy, which can be defined as follows. Xy of omega. Omega is a point of the even space. Omega is a sample point of the even space, capital omega. So it can be written as just like a function, x omega, y omega. So omega is the points of the 12 distinct outcomes. So omega can be 1 comma h, omega can be 2 comma h, omega can be 3 comma h, etc. Or omega can be 1 comma tail, 2 comma tail, or 6 comma tail. So 12, omega can be any distinct 12 outcomes, any of the outcomes. So if I take xy of 2 comma h, it will be x of 2 comma h comma y of 2 comma h. H denotes head and 2 is the number on the die. So head appears y. Y is a random variable. Look at that, y is defined as, if tail appears, if head appears, it will be 0. It will take 0. If tail appears, it will take -1. Whatever be the value of I. Whatever be the value of y. Look at that. It is defined like this. Whatever be the value of on the die, it doesn't matter. But if head appears, it will be 0. If tail appears, it will be -1. And x, what is the value of x? x will take the value on the die. That is, if the die shows 1, it will xih will be 1, x1h will be 1, x2h will be 2, x3h will be 3, and x2 tail will be 2. So it doesn't matter whether you have head or tail, it depends on the value on the die. So x denotes the number on the die, that is why the random variable. So now if you take x2h, that will be 2 according to the definition of the random variable x, and y2h will be 0 because if it is a head, y will take the value 0, and xy60, another omega subsample point or outcome 6 comma tail. So that will give you x6 comma tail will give you 6, and y6 comma tail will give you -1, because y, if tails appear, if tail appears, then y will be -1. The random variable value of the random variable will be -1. So that is how you can define the two-dimensional random variable x comma y. This is the example. This is the example how will you define the two-dimensional random variable. Now let us define the in a mathematical way, probabilistic way. Here it will be convenient to consider the two-dimensional random variable x, y. So we need two random variables x comma y. So there are so many problems involved where two-dimensional random variable should be defined. So let us define now. This is the definition. Let x comma y be two random variables defined on the same event space omega, capital Omega. Then the function x comma y from omega to R2, two-dimensional space, defined by xy omega equal to x omega comma y omega for all omega is the outcomes for the event space, is called a two-dimensional random variable. Just we explain this with an example, and this is the formal definition of the two-dimensional random variable. Okay. Now let me define some notations for that. Let me use some notations for that. So for ABCD belongs to R, all are real number. So the event -infinity less than x less than equal to A, comma -infinity less than y less than equal to B is used to denote the event. It can be written as like this. Small omega is a sample point or outcome of the event space capital Omega, and this can be written as -infinity less than x of omega less than equal to A, and -infinity less than y omega less than equal to B. So this is the notation. You may be encountered with this type of notations later on in the chapter. Next, x equal to A comma y equal to B, that can be written as x equal to A intersection y equal to B. Okay, it's just like it's both x equal to A and y equal to B, both the event. So it's, you are taking two-dimensional. And A less than equal to A, less than x less than equal to B, C less than y less than equal to D, and that can be written as in the similar way, intersection of both the events. So these are the important notations for your two-dimensional distribution. Okay. Next we'll define the two-dimensional distribution function. Just we already in the beginning of the probability we have discussed about the one-dimensional or single variable, single random variable distribution function of a single random variable, their properties. You know, there are a lot of properties. They're proving the similar things for the two-dimensional distribution. So what is the definition? The distribution function of a two-dimensional random variable x comma y is a function f from R2 to R defined by f of x comma y -infinity less than x less than equal to x, just like your one variable x. This was the definition. You know that the definition was this one, distribution function of a real variable x. It can be written as probability of -infinity less than x less than equal to x. Okay, just like your, yeah, there should be one probability here, probability of -infinity less than x less than equal to small x. Small x is the real variable. So that is how you have defined the probability distribution in for a one random variable, single random variable, when we are talking about a x only. But you have two dimensional random variable, so there is one another component for that, and xy belongs to the R2 two-dimensional space. It is also called the joint distribution function. So you have a different name here. You have to say joint distribution function of the random variable x and y. So let me give you one example for that. That will be better for you, for your better understanding. So suppose x and y, let me give you one example for that. Suppose x and y be two random variables. Denote the numbers shown by the first and second die. This is the first die, number on the first die, right? And this shows the number on the second die. Their random variable denotes the number on the first die and second die. So your event space will be like this, right? 36 possibilities. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, and so on, right? There are 36 event points, outcomes. So let me draw, let me put the points on this two-dimensional space. Okay, so these are the, look at that, there are 36 points. Okay, so you can denote it, this is by 1, this is by 2, this is by 3, 4, 5, and 6, right? And this is your y, this is your x corresponding, this is your, okay, this is your 1, 2, 3, similarly 4, 5, and 6. So fxy, if you denote, if you write fxy be the distribution function, f of x comma y be the distribution function of the two-dimensional random variable x comma y, of the two-dimensional random variable x comma y. If fxy is the distribution function of the two-dimensional random variable x comma y, we can find fxy at each point xy. So each point is your x comma y. Each point, each of the point in this space is the point x comma y. So we can find out the distribution function. For example, suppose you want f of 3 comma 4. Suppose you want f of 3 comma 4. So what does it represent? It means that probability of minus infinity less than x less than equal to 3 comma minus infinity less than y less than equal to 4, right? This is the probability. So that is equal to, actually this denote the region, this region, okay, this is the region actually it denotes. So 1 to 4 and 1 to 3, actually it's from minus infinity to 3, so you don't have any points beyond 1, so it's from 1 to 3 and 1 to 4. Y direction it will be 1 to 4 and exactly. So these 12 points, you check, there are 12 points, so your probability will be 12 by 36, 1 by 3. You can check that. So that is the probability. Okay, so it gives you 12 outcomes shown in the rectangular block. This is a rectangular block. It gives you the 12 points, 12 outcomes, and it gives you the probability. So it's a mapping from R2 to R. So that is how it is a mapping from R2 to R. It is a mapping from 2 dimension to 1 dimension, right? It's a point. So it's a mapping, it's a distribution function. Joint distribution function is a mapping from R2 to R. That is how your concept. So this is the example, beautiful example. With this example, you can find different examples also. Next, some properties. I will discuss some properties on that. So if f be the distribution function of two-dimensional random variable x comma y, if ABCD belongs to R such that A less than B and C less than D, then probability of A less than x less than equal to b, c less than y less than equal to d equal to this result. This probability can be calculated by using this distribution function. That you, this theorem, you can prove that theorem similarly, just like you have solved in the one dimensional case, that is for one random variable. You have proved this type of things, so you can use that. But I will give you the diagram for that. What does it represents? The region. The region will be look like this. It is a rectangle. It represents the rectangular region. This is the rectangular region. Okay, so no, it is just okay. Let me draw the rectangle. Yeah, this is a rectangular region. This point is actually A, this point is B. Okay, A to B, you look at that, your x will be A to B, and probability of y C to D. So this is your C and this is your D. So these are the points. These are the points A comma C. Okay, and this is your B comma C, right? This is your B comma D, right? And this is your A comma D. So it represents actually the two-dimensional region, the rectangular region x comma y. Okay, two-dimensional random variable x comma y. So this is the rectangular region. It's represented by this probability, and this can be calculated by this formula. Okay, you can check that formula. The proof is left for you. Okay, so next one is some properties. You know the similar properties of the random. First, one random variable for if you have discussed the properties for the only one random variable x, that is a single random variable. We have talked about the one dimensional distribution. So it is the same thing. Fxy is monotonic increasing or non-decreasing in both the variables xy. So this is number one. Number two, always, you know that probability distribution curve always lies between 0 and 1. It is the same property here also for two dimensional. So joint probability distribution also lies between 0 and 1. And f of minus infinity is 0 for both the variables x and y. And f of infinity is 1 for f of infinity comma infinity is 1 for all x comma y. Proofs are similar. You can try those proofs. And f is continuous from right with respect to both the variables. F is continuous from right. So distribution function is continuous. You know that for a single variable, distribution function is continuous on the right, and the jump discontinuity you can calculate. So it is a similar properties. Next, we'll define a very important definition, that is marginal distributions. That is the separate distributions, individual distributions functions fx and fy actually. So for x belongs to R, we can write this event as minus infinity less than x less than equal to small x intersection s. So this is your s is the certain event. This event minus infinity less than y less than equal to infinity is a certain event. So this intersection with this event, that will give you only this one. Okay, that implies that f of x comma infinity can be written as probability of minus infinity less than x less than equal to small x. Therefore, the new notation is fx is equal to f of x comma infinity. And what is your f of x comma infinity? It's nothing but your individual distribution function of x for all x belongs to R. Similarly, you can define fyy, individual distribution function of y, and these individual distribution functions of x and y are called marginal distributions. These are called marginal distribution. So you have a concept of new concept for a two-dimensional distribution function, joint distribution function, marginal distribution for x and marginal distribution for y. That is individual distributions of x and y. Now you can define the independent random variables. Just you have defined for a single random variable, and you have done so many problems on independent random variables. So independent random variables can be defined as probability of this minus infinity less than x less than equal to x, and minus infinity less than y less than equal to y, that equal to product of two distributions actually. So fxy equal to product of two marginal distributions. That is the condition for independent random variables. Okay. So there is a theorem. What is the necessary and sufficient condition? What is the necessary and sufficient condition for the independence of the random variables x and y is that fxy can be written as the product of a function of x alone and a function of y alone, where f is the joint distribution function of x and y. So if you write the fxy as a product of fxx and fyy, then x and y are the independent random variables. And if x and y are independent, then this probability of a less than x less than equal to b, this rectangular region, suppose probability of this rectangular region can be written as probability of individual a less than x less than equal to b, and probability of c less than y less than equal to d. So individual probabilities, multiplication of two separate functions. Now for discrete random variables, let us see how is the form of discrete random variables in two dimension. So if you talk about a discrete random variable, then your spectrum will be consist of xi, yj. So this will be the x minus 2 less than x minus 1. Just already we have taken for one dimensional distribution. So this is your y minus 2, y minus 1, less than 1, less than y naught, less than y1, less than y2, etc. So there are two variables actually, two spectrum points. So spectrum of xy is given by xi comma yj, ij 0 to plus minus 1 plus minus 2, etc. countably, at most countable. Okay. So fij, so you instead of fi only, because in one dimension for a discrete distribution we have defined fi, and fi equal to probability of x equal to xi, that is for a discrete distribution. Now in this case you have fij, x equal to xi, y equal to yj, ij equal to 0, 1, plus minus 1, plus minus 2, etc. And what is the distribution function? This is the definition of the distribution function for discrete distribution. Beta equal to minus infinity to j, beta runs from minus infinity to j, and alpha runs from minus infinity to I. And this is the ranges f alpha beta. And b comma d is not a spectrum point, then the probability will be 0. And if this, how to calculate this probability in discrete, probability of that rectangular region, so it can be calculated by simply this summation. Okay, so these are the useful theorems. Now how will you define the marginal distributions? Marginal distributions can be defined by fxx, fx comma infinity, just already we have observed that, and this is the notations for two-dimensional discrete distributions. Beta runs from minus infinity to infinity, alpha runs from minus infinity to I, and this is f alpha beta, and this is alpha equal to minus infinity to I, f alpha dot. Look at that, here you have a dot, f alpha dot, that is replacing b by dot. And what does it represents? Why the dot notation is here? The dot notation represents, the representation is explained in this notation, where fi dot is, it represents if summation j equal to, actually the it runs from j equal to minus infinity to infinity, fij, probability of x equal to xi. So that is the notation. Similarly, you can define the marginal distribution of fyy. Here you find f dot beta. So instead of I, there is a dot. So how will you define fi dot j? It is defined in the last line. Okay, so that is how your marginal distributions. Now two discrete random variables x and y are independent if and only if fij equal to fi dot into f dot j, fi dot into f dot j. That is the multiplication of two separate functions, individual function for I and j. So let's now define for the similar statements for the continuous random variable. For a continuous random variable, the joint distribution function fxy is everywhere continuous, and its first and second order partial derivatives are continuous in the whole xy plane, except for a finite number of curves of jump discontinuity in any bounded region. And the integration, double integration, you know that for discrete you need a double summation symbol. So for a continuous you need a double integration, multiple integration maybe. For 3 dimension you need a triple integral. For more than 1 dimension you need multiple integrals. So c to d, a to b, del to f, del x, del y, dx, dy is convergent. This is the multiple integration, double integration in this case. And the joint PDF, probability density function. You know that the probability density function is defined for the continuous distribution and probability mass function for discrete distribution. So in this case you have a joint PDF, probability density function, that is given by fxy equal to del 2f del x del y, where fxy is the joint distribution function, continuous. So some theorems, some properties. For a two-dimensional continuous random variable, probability of x equal to a, y equal to b will be 0 for all a, b belongs to R for a particular point a comma b. fxy greater or equal to 0, you know this is the conditions for possible PDF, that probability fx should be greater or equal to 0 and minus infinity to infinity integration fx dx equal to 1. So that is the theorem for double integration also. These two conditions are known to you, and this is the distribution function, joint distribution function for a continuous random variable, two-dimensional continuous random variable x comma y, and fxy greater or equal to 0. So these are the very important conditions for a possible PDF for a two-dimensional continuous random variable x comma y. Now how will you define the marginal distribution function for continuous distribution? Already we defined the marginal distribution for discrete distribution. Now this is the marginal distribution function for a continuous distribution, continuous random variable. So here you have an integration sign instead of the summation, and everything will be same. Okay, and fxx, this is called the marginal density function. This is called the marginal density function of x, where fxx is f dashed x at a point of continuity of fx. Similar definition for the y also, marginal distribution function for y, and you can define the marginal density function for y also, ffy minus infinity to infinity fxy dx. fxy is the possible PDF, probability density function for a two-dimensional random variable. So this is how you can define marginal distribution function for a continuous random variable and marginal density function for a continuous random variable. Now we can define the necessary and sufficient condition for independence of x and y. fxy should be a product of fxx and fyy, where fxx is the marginal density function for x and fyy is a marginal density function for y. Okay. Now let us give some example of continuous distribution, important bivariate continuous distributions. So you know that uniform distribution is there. A two-dimensional random variable is said to have a uniform distribution if the joint PDF probability is given by fxy equal to c for x comma y belongs to q, a fixed region, and 0 elsewhere, where if r is the area of q, if you know the area of the region, then c will be 1 by r. C can be calculated by 1 by r. So your fxy is actually 1 by r for all xy belongs to that region, and q is this rectangular region. Then the joint open. Then the joint distribution of xy is often called the rectangular distribution or uniform distribution, and it can be written as like this also: 1 by b minus a d minus c and 0 elsewhere. So you can define this way or you can define this way. This is the example of a important bivariate continuous distribution, uniform distribution. Let me define a more complicated form of a normal bivariate distribution, normal distribution. So look at that, it's more it is complicated one. There are five parameters: mu x, mu y, sigma y, and rho. Sigma x represents a standard deviation corresponding to x random variable, and sigma y represents a random variable corresponding to y, and -1 to 1 rho values of rho will lies between -1 and 1. And this is the expression. This is a complicated expression for a continuous random variable x1, and this is the diagram for bivariate continuous distribution, normal distribution, continuous normal distribution. You look at that, the bell shape is here. Here is a bell shape region you can see, and this is your plotting. This is your x direction, this is your y direction, this is your bivariate normal random, and you have 5 parameters: mu x, mu y, sigma y, and rho. And you can define the marginal density functions for x for a normal distribution. It's a similar to your normal distribution curve. Fxx is given by 1 by root over 2 pi sigma x e to the power minus x minus mx whole square by sigma x square. So this is x is normal, m comma sigma x variate, and y is actually, this will be y. Oh, this is a typographical error. Y is normal, my sigma y variate. Okay. So this is the so I gave you 2 examples for bivariate continuous distribution. One is a uniform distribution, another one is a normal distribution. And the diagram for the normal distribution, the marginal density function. You can calculate the marginal density functions for this uniform distribution also. Okay. So this is all about your part 1. So in the part 1, mainly we focused on the n dimensional distribution, that is distribution of more than one dimension. Marginal distribution, how will you define the marginal, how will you define the discrete distribution, and marginal distribution for the discrete distribution, marginal density functions for the continuous distribution, and so on, and few examples. Okay, thank you. You just follow my lecture for the part 2.